Hello, good afternoon, or good morning, or good evening, wherever you are. Welcome. This is the first in our series of connectivity webinars where we're going to give you a crash course in how to connect VTScada to Modbus compliant PLCs using our own built-in Modbus driver. My name is Chris Little. I'm here in our Bedford office in Bedford, Nova Scotia, and joining me is Blair Sooley, whom many of you already know. He is the hi Blair. He is the regional account manager for our Houston office. Is it still thunder and lightning there, Blair?
No, it's perfect now. Get lots of sun. Everything's beautiful, nice and warm. How's things up in Canada?
Oh, it's perhaps the first warm day we've had in as long as I can remember. So it's a great day up here. Blair is going to be doing the heavy lifting today, and my job, he's going to be doing all the presentating and PowerPointing, and my job is just to interject sometimes so he has a chance to drink a sip of water or take a breath. So today we're going to move really, really quickly. We've got 30 minutes to deliver a complete crash course in the VTScada Modbus driver. And so one of the ways we're going to do that to stay on that timeline is we're not going to answer questions in the body of the webinar, which in the past we have done. I'm sure most of you are aware, on the screen right now, somewhere around there is a little dialogue where you can enter in any questions that you have. So type them in as soon as you think of them. The system records them. We sort of keep track of them and sort them. And at the 30-minute mark, we are going to answer all your questions. So if you have to go at 30 minutes, you're not going to miss anything. Because at the end, we're going to send everybody a link to the slides. We're going to send you we're going to send you the slides to the video, and also a list of all of the questions and all of the answers that we had. So you're not going to miss out on anything. And without any further ado, I hand you off to the capable hands of Blair Sooley.
Thank you very much. Appreciate it, Chris. So yeah, we're going to look at the integrated compliant Modbus driver. I'm going to turn off my webcam there now, just so that we're not going to take up any of your screen time. All right, that should turn me off. Hopefully you can see that. Everything look good now, Chris?
Looks good.
Okay. All right, so let's operate into this. So as we're going to go everywhere from the very beginnings here of what is Modbus. I'm not going to spend a whole lot of time on this because, again, we got this 30-minute time cap we really want to keep within. Modbus was created in '79 and was really designed as the first major protocol for industrial comms that was utilized for people to communicate from PLC to PLC, from PLCs to communicate with computers, where at the time were not much of a thing. It's simple, read and write. That's the whole intent of it. Keep it as simple as possible. At the time, it was the height of new concepts, and since then, technology changes. You're talking major changes to computer capabilities, major changes to networks and such have really pushed the new protocols that are out there. But in doing so, we've still got a lot of people who want to maintain the use of Modbus because it's still incredibly common. So as a result, even though it is a standard, we end up with a whole lot of variations of this standard. We're going to kind of touch on those things. We won't be able to answer a whole lot of questions about those, but we will be able to follow up any questions you do have. So I'll just skim across a number of topics as we go here. It's also it supports a very simple object type. It's your discretes and your analogs, inputs and outputs, nothing more. Publicly available, documented. You can get right down off the modbus.org, and it's royalty free. So again, it becomes very reasonably cost to implement. The physical configuration. This is going to be a kind of a standard format we're going to create for these types of presentations. So it may change slightly from this one on, but this is our first kick at this. So the physical configuration, you've really got two major pieces that make up Modbus comms. You've got the Modbus slave over in the left-hand side. That represents your field device, the devices that are gathering your equipment information, doing all your field controlling and such. And then you've got your Modbus master over on the right-hand side. These days, that's represented by a computer system, VTScada, for example. In the middle, you've got your wired and wireless options. So your methodology for communicating between one device and the other. You see there's a ton of different options that are out there They pretty much span the entire list of everything that's available today, and even some that are kind of defunct. So you're seeing everything from serial connections to Ethernet, which is the most common these days, seeing daisy chain mechanisms, all the wired options, and then wireless. You get into Wi-Fi and cellular and serial radios and such. In order to set this up, is there any additional pieces that are required? The good news is no. There is no special hardware required unless you're using one of these daisy-chained wired specialized systems, most of which are now not utilized anymore. Is there any special software? None. That is because we have the built-in Modbus driver, and thereby you don't need to set anything up other than your network connection between the two devices. Okay. So what are the pros and cons of utilizing this protocol? Well, we'll look at the good stuff first. It's easy to learn. It's incredibly easy to configure. It's very easy to maintain. There's not really a whole lot of a learning curve to Modbus. You see a value in your PLC, you want to read it, you connect in via your software, and all is said and done. You're now good. No special hardware requirements, as noted. And it's common across many field devices. That's great as long as it's actually common across those field devices. So there's a lot of devices that utilize Modbus, and what you'd like to do in many cases is you want to create one network that brings in all of your devices. If you can now use the same protocol for all those devices, then fantastic. But why not use Modbus? Well, it's non-standard in a lot of cases. So while you may throw in 3 or 4 different devices, all of which utilize Modbus protocol, they may have differences in them. And thus, when you've configured one device to communicate, you may end up with other devices that in fact cannot communicate using the exact same configuration, which can be extremely confusing to people. It's inefficient. It's a typical polling protocol. Keep in mind, this was kind of at the start of this world. So in polling, what you do is you request data from a device. It responds by giving you exactly what you requested. The next time you request data, you ask for the same data. It responds with the same data unless something's changed. The result is that you may end up with a continuous flow of no new data coming back and forth between those two devices. So it can be incredibly efficient in polling. There is no report by exception methodology available within Modbus, that being the ability for a device to say, I've got something important to tell you and I want to tell you now, so I'm going to send a message out to you. Okay. There's no data logging capability, and we're talking about the standard Modbus here. There's no data logging capability, so there's no ability to throw in a log into your device and then read that data log from your device. There's no time stamping. So let's say we're polling a bunch of equipment and we go around a circle polling 10 or 15 or even 100 devices, and it takes us a while to get around there. We can have something occur that no one knows about. Not only do we not have the ability by report by exception for it to tell us it's occurred, but we don't know when it happened during that period that we weren't communicating because we don't have a timestamp on that data piece. The addressing is purely numeric. This is not a big deal, but there is a lot of the new protocols that push that are using text-based addressing, such that you can quickly see what an address means. In Modbus, it becomes a very simplified numeric value. It doesn't necessarily mean anything. Does not support the browsable addressing. Again, a new technology in protocols whereby you can read in the entire database of data available, and then read the values that you want.
Blair, before you go on, I have a quick question.
That was my taking water. Go ahead.
So given that the technology has changed so much, I'm a little bit in marketing, a little bit at arm's length. For most new systems going in, what is, roughly speaking, is there a lot of new Modbus systems going in, or is it mostly the sort of conversion of existing ones?
No, there's a ton of new Modbus stuff going in. There's new devices that are out there all the time. One of the biggest changes that we've seen is a lot of devices that used to use a number of different protocols are now utilizing the Modbus standard to make its data available. So, for example, diesel generators. You'll see a lot of their ECUs that gather their data will now have Modbus as an option, whereas before they used to use some CAN bus standard or some other standard in order to communicate. So it's actually just as popular, if not much more popular than it used to be.
Thanks.
You're welcome. So when reading and writing Modbus register values, this is kind of the summary of what you need to know. The I/O types that you can get, as mentioned, you're talking inputs and outputs. Very simple. Here's your coils, which are your digitals. Here's your registers, which are your analogs. And data logger, we'll talk about that in a minute. That's a non-standard piece. The 5-digit address is the most common methodology you'll hear about. And you'll notice that it starts at 4 zeros and a 1, goes to 09999. Due to new technology advancements, there was an additional 6-digit addressing mechanism added so that you could now start pulling additional data well beyond what was available through the 5-digit addressing. As a note, anyone who's looking at this should note that this was written incorrectly in our documentation, so it needs to be fixed. This is a text prefix set. This is 4 different addresses, simply a different addressing system that directly replicates what is available through this 6-digit addressing scheme as well. A different mechanism for doing. All are supported within VTScada. Okay. Once we get our data, it's important to note that when you request data from Modbus, what you're really getting is a 16-bit value, a register. That's all it was ever meant to handle. Sending back was a 16-bit register and a certain number of those such registers. So when we get the data back, it's important to understand how do we want to utilize it. We want to utilize it as just a simple unsigned byte or an unsigned word, for example. Then we just read it in and we use the data as is, as an integer. You can scale it and such within SCADA systems, but oftentimes you want to interpret it differently. So for example, with a floating point, you may use the actual data float point, 32.9, for example, within the PLC. That value can then be read from the variable, the 4 bytes that it represents within the registers. And by putting in these suffixes, it tells VTScada how to interpret that piece of data that you've just read in, how to show it on a screen. So you'll see a massive difference in how you would represent, say, a 32-bit integer versus a floating point, for example. Okay, so you'll see these. If you're representing bits within an address as well, then you can call those by putting in the address, the register, if you will, and then slash and the bit number. For example, 0 will give you the first bit within the address. Then read-write options. So this is where things got confusing. If it wasn't already confusing enough, they then added in these additional items. The original Modbus standard was written with big endian, which was the order in which the bytes are received. They are interpreted as most important information first, most important byte, followed by second, the least important byte. That wasn't always the way. So following that, things changed. You ended up with registers that could be read in and reversed. So for here, example, single register values, this reverses the byte order. This reverses the byte order for certain double register values. For floats and doubles. This reverses the byte order for long integer registers. All of these are there, and they're all within our driver. If I look at a driver here, I'm going to switch over to VTScada so you can see. And if I look at a Modbus driver, for example, you can go into the options section and you will see these 3 options. This does nothing to change the actual data or to manipulate the actual data set. We still get the raw data in, we still interpret it, we interpret it in a different way, and therefore we display it on the screen in a different way. That's the only difference. There's no manipulation of the actual data. Rewriting the outputs, this is a nice addition, and again, it is under the options for storing the last output values and now enabling the rewrite. What this does is to allow where field devices do not hold the memory of the last output values. So for example, you've got a coil that should be held on all the time, for example. You can set that output value by VTScada automatically. You can just hit a button there and manually ship out all your outputs. You can also, if you had something like a register set that represented a recipe for a process, then you could hit a button and output that same set to a PLC if you, say, replaced a card within it or the main CPU within it. So let's go to demonstrating this thing now. Now that we know what our PLC looks like, and we've got a set of registers that we want to read. Go ahead.
Take off down that road. A number of people have sort of come in at various points through the introduction that you just did, and I just want to say to everybody that if you came a little late, with the whole presentation, the slides, and the recordings, and all of the questions and answers that happen at the end will be sent out to all the attendees. So whatever you missed, you can easily catch up on later. Sorry. Thanks, Blair.
No problem. So I'm going to create a new app just right from scratch, and I'm going to connect into a Modbus PLC that is being simulated in our office in Canada. I'm down here in Houston. I'm going to pull data across to our VPN so you can see how that might be done. So we'll just create a brand new app with nothing in it. And we'll start the application automatically. Shut this one down.
You'll notice VTScada can actually more than one application at the same time, so long as you don't exceed your total tag IO tag band.
Yeah, so I'll go into the tag first into this screen, and I'm going to clear up a bunch of stuff. So I'll just grab everything that's on the screen. I'll delete that, and we'll go back to developing the tags. So right from the beginning, what I want to do is create three pieces. One of them is going to be the port that represents the connection, the physical connection. That's the piece I had in that either wired or wireless options. The option for connectivity we have here with this specific simulator is a TCP/IP connection. And so we're going to create a TCP/IP tag. So I'll go into the ports, tag types, select TCP/IP, and I'm just going to call this my port. Keeps it real simple. Now under TCP/IP name and address, I'm going to put in the address here of 10.158.32.11, and under the port number, 502 is the typical address for Modbus, but we use 501 periodically if we're doing simulation stuff. So in this case, we got a simulator running. I'll hit OK, and when I do, what you'll see is that, expand this out so you can see a little bit. You'll see the address has had the port attached to it as a suffix, and that becomes the connection that we establish. You'll also notice that the value is not filled in yet. There's nothing here. That's because we don't do anything until we're actively requested to do something within VTScada. It makes us more efficient. We don't try to set up the port until there's something to do with that port. So I'm going to take the port now and add a new child to that new child tag. And we'll make that tag a driver. We'll go to our Modbus compatible driver. And under Modbus compatible driver, I'm just going to call this my driver. Very inventive. Under the options, I have a number of comm channel options here, and I'll show you those in a second. I'll discuss them, but for now, I'm just going to choose the Open Modbus TCP. Okay, I'm not going to set any of these things here because my my simulator follows the Modbus standard exactly. And then under serial, I'm going to choose the port that I've set up. So I go into here and I can choose any ports that are available. Here's my port. I hit select, and the PLC address is its address on the network. So Modbus network addressing can be anywhere between 1 and 255, I believe the addresses are. So I'm going to just select 1, which is just a first point on this Modbus network. I don't set up any of the rest of this at this point. This gives me information on how many times I want to retry my connection. So for example, if I have a poor connection and I think we may be able to establish connectivity by trying again, I'll set up a retries number. You don't want this to be too high. It's unnecessary to go too high. If it's broken, it's simply broken. Timeout limit, this is how long it tries before it considers it to be a timeout. And therefore, it'll wait and it will try again. It'll wait this period of time, retry, delay, and then try again. Okay, so I'm just going to OK that. Now I have my driver, and my driver, again, does not have a value. The reason is I'm not trying to do anything with it yet. And add a value in to try to pull from my PLC now. So I'll add in an analog value. And we'll go to an analog status tag here, and I'm going to call this my analog status. Under my driver, I want to choose, I could have done this, had it choose the driver automatically, but I did want to show you selecting my driver as the IO point to get data from. And now I'm going to put in my address. This is where we go back to our list. And in this case, I know there's a value at 40,006. Now I could put in / unsigned word here, but I don't need to because the default is to read it as an unsigned word. So I will leave the scaling off so we see the data raw the way it comes in. So I'll put in a value of 1,000, and its scaled value will also be from 0 to 1,000. Okay, no need for an engineered units here. I'm just reading in some data. Take a look at it. And now I should be establishing the connection into my PLC, and I should be seeing data show up at my address. I've got a scan rate set up about every 1 second or so, and I believe it's actually set to 1 second. So we're going to start seeing the value increase on a regular basis here now. Okay. And if I now take a quick look at a plot of that data, you will see that for the last 2 minutes, you'll start to see that value climbing. Okay. All right. So I've now got my data on the screen, and that worked out great. Everything is working perfectly. Well, it doesn't always go that way. So let's look back at when it doesn't go there. What happens now? We get into diagnostics.
Just before we do that, I just want to say, Blair, you are at 8 minutes. 8 minutes to go.
Oh, I got lots of time. We're only diagnosing Modbus.
You're really quick.
Problem-solving tool.
I thought.
Okay, so Modbus error codes. Let's look at what those Modbus error codes might be. I will take this value, my driver. I'm going to change my driver settings, and instead of pulling data via Open Modbus TCP, I'm going to change the protocol type that we're selecting. And when I do that, and I look at my port, I now have a value for my driver of 517. Okay. There is a list of all Modbus error codes that you run into over in our documentation. You can either look the one online or the one that comes built into VTScada. And if I look down at 517, I will see that it's timed out waiting for a response from a remote. A common type of a problem that you run into when you're trying to communicate and you have problems with your network or your general setup. So that's when you start digging in. You'll see other things that represent illegal memory address. So if I was to try to read a value of 96999, I would receive an error code on that, for example, as well. Okay. Now there's a couple of other nice built-in pieces of built-in tools, the driver statistics, which gives me the current status, error counts, and time and date of the last error. And then the driver comms, which give me the real-time display of the current send and receive data. So I'll just throw those on a screen so that can help us. Okay, draw that. And we'll draw diagnostics here. We'll draw comms. Throw that button on the screen. I'm going to also throw the other one that we talked about, which is stats. Throw that one on the screen. And now I've got two buttons. This one is my statistics. So we look and we say, okay, we got an invalid timestamp. We have an error of 517, timed out waiting for response. And we can see our count is going up every second or a couple of seconds, indicating that we're continuously failing. Okay. I go over to my comms now and I can see that I'm transmitting out data and I'm receiving no data back. Okay, so this all kind of falls into place with one another. This is good diagnostic stuff. And this is the kind of thing you're going to get into and start dealing with our support team. The first things they're going to do is start to understand what's happening here. Okay, let's show you a couple more diagnostic tools. So under the driver trace, if we need to get a longer history and see maybe where errors are occurring, if it's not something that's continuous, we might need to see the history of it. So let's look at what's called the RPC diagnostics. We bring up Trace Viewer, and Trace Viewer has a couple of options here. Here's our RPC diagnostics, which is going to help us define, identify which computer is the server for this Modbus driver. I scroll down here under services, and I'm seeing at the bottom of this my driver. Okay, let me look in deeper into that, and I'll close that. I don't want to see it now. Scroll down, and I see that Blair's Dash laptop, so that's my station I'm on right now, is the server for it, and that I have no additional servers in my list. Okay, so that gives me one detail of who's doing what. I'm going to look at the log of all of the data that's going back and forth with the driver. So my driver trace for my app 2, the application that I built. I'll hit close, and now I'm going to look right here at select the drivers, and I can select any of the drivers within the application or all of them. I'll select them now, and we'll start to see data that will pop up, and you'll see here sent and received for each time I send out data and the data coming back and forth. I'm getting nothing back. Okay, so let's fix that. We'll go to the properties for my driver now, and I will set Modbus TCP. Now I've fixed that driver, and I should be able to see that my RPC diag is now fixed. I'm getting this good sent data. My return received data should start to show back up. So while I'm waiting for that to happen, I'll pop over to the presentation. We'll come back to that in a second. Okay, so designing for efficient comms. What happens with designing for efficient comms is that typically here, you lay out your addresses and then you go and read them. And then we get complaints about high polling times and high data use and such. The reason this happens is because the read messages gather, because you have one read request here for coalesced analog register groups. So you look at these registers and they say, well, we're between 101 and 125. We can send out a request for 30,000 group. And the maximum read block we can get, these fall within it, of 125 registers. So we'll create a read for that. We'll create another read request for analog register 40,100, this one. Well, it's not within 125 registers. This one is not. So we are going to create another read block, read request for 40,315. And then we got a final one to request the 10,000 group. Okay? We end up with a very inefficient 4 read messages requested. Got our high polling time. We've got high data usage, which can be bad on, say, a cellular connection. And we get a lot of data in between here and here that's returned that we essentially are just throwing away because we don't care about it. Well, if we instead changed it and had the registers all next to one another, and very well organized in a read block. So we copy them from here to here before we read them. Then we have a VTScada read message that coalesces that group into one single read, 4101 through 4105. We got very efficient. It cures all of those problems that we've had in the previous one. Let's run back here and see if we've got comms, and we do. We've got sent, and we got received for each of these. So all is well now. Okay, so we don't need to log that anymore. I'm going to turn off logging here because I don't want to use up CPU. There's no need for it. Modbus variants. These are the Modbus variants that we could have chosen. We chose the Modbus TCP. This is the original Modbus ASCII, which is the legacy type. It's not used very much anymore. Modbus RTU is very common, used for wireless comms, specifically designed for serial comms over wireless, like serial radios. This is embedded Modbus. Becomes very useful if you want to have a serial device that's speaking Modbus, Modbus RTU in particular, that you encapsulate in a TCP packet. VTScada can then extract the Modbus RTU from the TCP packet and read the data. Okay. Finally, we have our Modbus TCP, which is by far the most common implementation for, this should be for wired applications. I should have said that. That was a mistake on my part. And Modbus Plus. Sorry, what was that?
We'll fix that in post.
Okay.
And also, we are at 30 minutes.
Yes, I think I'm on my second last slide. So, legacy support for Modicon. He's so good. He's keeping me on track. Legacy support for Modicon proprietary control network. So this was one of their own versions that they created at a time when there was no standard network types out there like Ethernet. Modbus was designed to allow for extension. So where things would not fit perfectly in the standard, they created a capable, an area that they're defined as user-defined function codes. Only one device that we know of did a really good job of implementing that, and this was the Control Microsystems group, which they created a SCADAPAC D-log function for data logging. And then there's a whole bunch of non-standards. This is where things get kind of ugly, when you start having to deal with non-contiguous addressing. This was never allowed. This is in some devices that we've seen. Single address reads instead of being able to read blocks, also non-standard. Byte order manipulation, non-standard. Enron Modbus for oil and gas, with all kinds of different non-standard pieces that never followed the user-defined function codes. And then you get newer addressing models, the 6-digit and the HC1 type addressing I was referring to before to extend the data range. All of these things non-standard. So I want to finish up with a component that's built into our system and is in fact what we're reading data from at the moment. This is what we call the virtual PLC, virtual I/O, through a Modbus virtual PLC. When you enable it, you create an area that replicates what the Modbus standard does as if you have a PLC within your computer. You can read from that device, you can write data to that device. Others in other products can read from and write to that device as well. It gives you the benefit of having two SCADA systems, one being VTScada, one being something else, that can provide intercommunications, and without having to dig into specialized protocols beyond Modbus, or having to request data directly from each other's historians or such. So that is built in, and as noted, that's exactly what we're doing for our demo here. So that was my last item I wanted to touch on. Hopefully we've given you a good understanding what Modbus is, how it's implemented in VTScada, and we've touched on some of the things you were hoping to learn. Now it's open to questions. If you'd like to throw out some questions there, I'm more than happy to answer all I can, and those that I can't, we'll take back to our engineering group, and we'll get back to you with an answer.
That's great. Well done, Blair.
Chris, you want to take it from there?
Thank you, sir. I'd say that's on time. It turns out we only have a few questions, so if anybody has any more, feel free to chime in. First question is, are you planning to support the Modicon Unity addressing, i.e., question got cut off a little bit.
The text-based addressing, I believe it's what it's called.
Yeah.
I do not know. I think that's probably one for the engineering team to answer. I don't know if it's generally available for support or if it's a proprietary protocol within Modbus. Within Schneider.
Right.
So I can't answer them.
Okay, so we'll get a fuller answer and include that in our Q&As that we'll send everybody. The next question is, when setting up multiple locations where tags are in a context, do I need an individual port and driver for each location, as they will have, so my window's a little bit small here.
Okay, so I understand what's being asked. The question really surrounds what is the communication methodology. So if it's a TCP, then you would have an individual port for each of your devices out there in the field. And you would also have an individual driver for each one of the devices in the field. If it is a serial communication link where you're sharing something like a serial radio, which polls from one to the next, you would share a single communication port, and then each device would have a driver. That also takes advantage of a feature that we have within the system, which is called the polling driver. And those of you who probably have seen the polling driver before, many of you, I'm sure. I will add in a new child here. And it's within the drivers group. The polling driver is the ability to create a semaphore. So a semaphore is essentially something that passes the torch to each subsequent station, such that they can all only one of them can have access to an asset, or in this case, a COM port at the same time. So for each station, you would have a polling driver. They would be part of the same group name, and each one would have its own Modbus driver as well. I would put in the station I want it to be here for station number this, and then I would take my driver and link it to my polling driver. So each location would have a polling driver and a driver tag, yet they would all share the same serial port.
All right, good.
Any more questions there, Chris?
Yeah, all right. And thanks for the class. You are welcome. Can we access DMP3 devices? Yes, and that's probably a good time to say two things. One is that on your GoToWebinar interface on your screen right now, there should be a part called Handouts. And on that, there is a copy or a link to our full device driver list. So you can go through there. This webinar really just does focus on one thing, but I don't want anyone to think that that's the only driver that we have built into VTScada. We have over 100 of them. So please have a look at that. It's also on our website. I'll take this opportunity to say that the next two parts of this connectivity series will focus on. The next one will be May 22nd, and it will be on VTScada's JSON driver. So pulling in data from third-party databases, from websites, and bringing those into your SCADA applications. And then in June, we'll be using DF1 to connect VTScada's Allen Bradley Micrologics PLCs. So right now you can go to our website under the events on the right-hand side. There's a link where you can go in there and sign up. We already have lots of folks there already. But I'll let Blair add anything else he wants to that answer.
Yeah, DMP3 is definitely a protocol of great interest in a number of industries. Obviously, very common in the power industry. It's become more common most recently, more common recently in the water industry, and it's also, oddly enough, become of interest in the oil and gas industry. Others, I'm not sure about. But as a result, we're definitely focused on that. We have a full DNP3 driver suite built into VTScada, and it's been tested for many years. Works in a lot of locations. We deploy DNP3 all the time. And this was one of the specific drivers I pointed out to Krista. I think it would be very valuable to have one of these seminars on so people could get an understanding of how it's done. Modbus is not a complicated driver. DNP3 has a lot of capability. It goes well beyond any of the things that Modbus is capable of doing. As a result, it could be, I'm thinking that somewhat of a longer or multiple part one could be much better off for DNP3.
Yes, I think absolutely it'll pay to break it up into manageable chunks. So that's great. Another good question here is, how is all this data secured?
So you mean, okay, there's two different pieces to that. One is
PLC.
What's that, sorry? Chris?
They're asking, how is the data, presumably the data being passed back and forth between the PLC and the SCADA system, how is it secured?
Okay, there is no security mechanism built into the Modbus standard. You would have to do something outside of the standard itself to allow for that. Modbus was developed well before security on links was considered, and there are some limitations in that respect, and some people have come up with ideas since to do point-to-point encryption, so that you would just simply speak to a device with an encryptor on one end, a decryptor on the other, and the data would come out. On both ends, they wouldn't care what was happening. In the middle, the data is encrypted, so it would be unreadable by any device that was able to sniff the data while it's being sent back and forth. Similarly, if you're doing something on TCP, then you can use a VPN IPsec tunnel, which is very common. That allows you to do encryption at point-to-point encryption for these links, and we see that quite commonly used. But serial is still kind of an unknown, bit of a Wild West world, so serial over radio. There are other protocols that utilize security, and Modbus is just not one of them.
Gotcha. And I think the last question is specifically, I guess it's a bit truncated, but specifically control microsystems SCADA packs. I'm assuming they're asking that we can connect to that specifically.
Yes, absolutely. We do comms to control microsystems SCADA packs all the time. They're one of those units that requires a couple of specialized settings in the reverse flipping of the bytes. And I highly recommend, if you're setting up anything like that, if it doesn't work right out of the box, you can either play with those settings or you can give our tech support a call, and they've worked with a lot of these devices, so they might know right out of the gate which ones to set. Control microsystems they deal with on a very regular basis.
Great. So if people want more information, if they want to work on this on their own, in their own time, in addition to watching this video again, what would you recommend people do to continue on from here?
Well, as was recommended to me, if you want to know everything there is to know about the Modbus standard, I was told by one of our engineers today, read the standard. And was subsequently sent a copy of the standard. So if you really want to do it, it's generally available. You can download it, you can dig right into it. If you want to know the specifics of how it's implemented by a particular product, you're going to have to do some digging. Most don't usually identify where they differ from the standards. So it's only when you start setting up the comms that you quickly find something might be a little bit off, and you've got to start playing with settings. The good thing is you're not going to mess anything up in the PLC by playing with the settings on the VTScada driver. You can just connect to it and try every combination of settings you can find until you get it right, or you can phone the manufacturer of the product and dig in from there.
Also, I suppose it's helpful to point out for people who, I see a lot of familiar names on the attendee list here. Thanks everybody for sticking around. We still have almost everybody we started with. But if you're not a customer right now and you want to try this out for yourself, we actually have a 90-day trial for a large tag count trial. And we also have a small tag count indefinite license, like a free industrial license for under 50 IO. And you can go right to our website and download that and start working your way through the tutorials in the onboard help. And other than that, Blair, I don't see any other questions other than a few more people who said thank you, and to all of you, you are welcome. Thanks everybody for sticking around this long. Blair, do you have any closing remarks?
No, but I look forward to seeing you guys at the next one of these. It may be me, it may not be, but appreciate you coming. And we hope to have many more of these in the future. If you have ideas for where you think one of these short technical seminars might be appropriate, please let us know. We'd be happy to look into it.
Great. Thanks, everybody. Have a great afternoon.
Take care.